are we taking that quiz today? The week-long quiz?
So the week-long quiz will be sometime today.
Sometime today?
Yeah,
Okay.
it will be taken out of class.
I don't know really what. I'm severely colorblind, and it's hard for me to do the resistor problems because I'm like, okay,
yeah.
I know if it's, you know.
I'm trying to think. Send me an email to let me know, and I'll just double check to see. And if there is, let me see what I can do about it. Try and take it, and then just put on it. Colorblind, can't tell what this is. Just make an assumption of what you assume.
Make an assumption. Okay.
Yeah.
Yeah, it's like purple and blue and green and red.
I didn't think about that. So thanks for letting me know. If you're okay, just sending me that, and then.
So just take the quiz, and then I'll email you after.
Yeah. Sounds good. Thanks. Canvas. Okay, so there seems to be a couple errors in some of the attendance quizzes. So if you do find an error, there is extra credit under the discussions. There's this extra credit spotting error. Go ahead and take like a screenshot of which problem it is, what it's going with. First one to post it can get extra credit for spotting those, and then I will get those fixed. For those that, if it is like this, which was the attendance one you were doing? Was it number 2? Yeah. So second one, there is a couple, like, I guess some of the images aren't coming through sometimes. Let me know those situations. Different operating systems, things go wrong. So do let me know if some of those do. If there are things you can assume what it is, just try and do it. And then if you can, I'll fix things and I'll send an announcement that they're fixed, and then you can take those. If not, just do them, and then we'll give you guys credit the best we can. Go back in and do them, okay? Discussions, yes. So the extra credit spotting errors is under discussions on there. All right, learning objectives today. We're going to go over, in general, we'll do parallel versus series, nodes, understanding nodes, moving to unique currents in the circuit. Now we have multiple elements in the circuit. We're going to talk about that. And then moving to understanding the currents in the circuit and voltages throughout the circuit. Understanding loops. And then we're going to move to power. Did not put power on here. We are going to cover power today. And then Ohm's law, KVL, and KCL. So you're going to learn the 3 main techniques of the basis of analyzing circuits. So those are going to be our goals for today. All right, so terminology is where we're going to first start. So in your book, it has lots of different terms. The main ones that you want to make sure you understand is what I'm going to term an ordinary node, an extraordinary node, a path, a loop, and elements that are in series and parallel. So these are the terms, again, that you really want to make sure you understand. The other ones are not as important right now. So what is an ordinary node? So here is a circuit, and what we recommend is color coding each of the wires in between 2 elements. So you're going to look at an element, and an element such as this is an AC source. You can see the little squiggly in the middle. That means it's AC, alternating current, so it's a sinusoid. DC is when you just see the plus minus. That's going to mean more like the battery. So for that source to the resistor, there's a wire in between there. So again, it bends. Remember, it doesn't matter that it bends. It could be straight and still mean the same thing. So we color in between an element till we hit the next element. Here we have a resistor, and as I go, I hit another resistor, so I stop, but there's another wire off that, so I make it to the other one. So you're going to color code every wire in between every element. When you have connected to that wire only 2 elements, that's called an ordinary node. So the definition of an ordinary node is going to be only 2 elements. In contrast to that, at this red wire, I have R1 as an element connected to it, R2 and R3. So that is how many? 3. So 3 or more is an extraordinary node. So that is the definition of ordinary and extraordinary. A path is going to be between 2 extraordinary nodes, yes.
So there can be more than 3 for an
Yep.
extraordinary node?
You can have many, many if you want.
For the ordinary node, does it have to be a bend in the wire, or is it just going to be a straight wire?
Remember, it doesn't matter if it's bent, straight, at an angle. That's just more a physical location. So yes, just as long as there's 2 elements, that's an ordinary node. Yes?
If it's just one element, is it just a node?
It's a floating node.
Oh, okay.
So it will still be a node, but it won't be ordinary or extraordinary because there's no more elements on it. So it will just be a node. And there'll be no current going through it because it's open, correct? All right, so path. A path is going to be a continuation between, or I think it's easier just to think between 2 extraordinary nodes. No, I can't spell extraordinary nodes. So, in this example, hopefully you can see what type of node is that ground node. Ordinary or extraordinary? Correct, extraordinary. So between that ground node and where it's labeled, so this is an extraordinary node, N1, you have different paths. So one path is going to be from N1, it goes through all these elements, and it pretty much contains all of these too. And that would be a path from that N1 node through R1, through the voltage sources, so the AC and the DC voltage sources. And so that would be one path. Another path would be through R2 and L. L is going to be an element we'll learn in 1230. It's called an inductor. But that between those 2 elements is another path. Between N1 through R3 and that capacitor to N2 is a path. Between this N3 and ground, this will be a path. It only has R6 in there. Between between N2 and the orange one, N3, there's also a path. And between the N2 through this element, there's a path. And it just has that one element in there. That's called an op-amp, which we'll get to when we get to digital logic. We'll learn about that one. That's your last unit, 3rd unit. So all of these paths have unique currents in them. So that is the takeaway. Once you identify what a path is, that will tell you you have a unique current in that path. So every path has a unique current. So how many unique currents? Well, I'm not going to ask that one because this is a tricky one. There's actually no current because of the op-amp characteristic in the R5. So I'm going to skip that part there, but the other ones all have unique currents. What that means is that you have one specific current going through R1. I can label it like I1. It's going to go in the same direction through these current sources. All of these will be I1. Here, I chose this direction arbitrarily. So if I don't know what it is, because I don't have a current source in that pathway, if I have a current source, I'm going to have the fixed value of the current source. But if I don't, I can arbitrarily label a current going one way or the other. I solve the circuit and that gives me the answer. It may be negative, which is fine. It just means like, oh, the current's actually moving conventionally in the other way. So that's what that means. So in R2 and that L, I don't, again, know a known current there. So I can arbitrarily label it. I can label it right next to the element. I can label it next to the wire. I can label it on this side. All of those are the same, meaning that through that path, I have one current. I'm going to give it a variable name. I'm just going to call it I2. And so on. So these are that every element in a path has a voltage and a current with it. So across R1, there's also going to be a known voltage across it. Yes?
Can the voltage sources help us determine the direction of the current because it goes from high to low?
Correct. So you can make an assumption that if there's a current source, so I did arbitrarily label this, but also with a little bit of knowledge in that it is most likely going to flow from the positive terminals of these back to the negative. So that's why I drew it in that direction with a little bit more educated guess. But again, if I don't know and don't remember, I can label it, solve it, and then look at what the answer is. So with the voltages, I know what they're given as a voltage. So that element has 6 volts and I1 going through it. Again, I1 isn't known right now. The resistor R1, I have a voltage across it and a current. How do I label the polarity on the current again? What's on the left side of it? Good job, positive. And then on the arrow side, correct. So I can pick my voltage across it going the same polarity if it's not labeled. So usually for a resistor, you'll want to put it the same direction as the current that you're defining if you know what it is already. Again, if not, you're going to find out it's opposite when you solve the circuit for the voltages and the currents. Okay. All right, a loop is going to be a closed path, meaning that you're going to go through different pathways from one point to back to the same point. So if I pick, say, ground, and I want to take a pathway, I'm going to take it going around this direction. That's one path to get to N1, and then at N1 I can decide which direction to go. I can either go down through that path back to ground, or I can go to the right and go back to ground that way. At each extraordinary node, I just make a decision, which way am I going to go? So one loop would be from ground to N1, and then back through this pathway back to ground. So that would be one pathway. A different pathway would be going the same way to N1, but this time go through in R3 and keep going through these till I get to N2. Then at N2 again, I could have 2 different pathways, so I can decide which way to go. I'm going to just arbitrarily choose this pathway, which gets me to N3, and then I could go through the op-amp to ground, or again, I can just go down. So it gives me, every single one will give me a pathway to get back to ground. Why did I stop here at this location itself? What location is that I stopped? It's ground. Does it matter if I stop on the right side of ground, in the middle of ground, at the label of N4 at the ground, or at the bottom of the 6 volt? Doesn't matter. They're all the same location. Okay? So voltage at that is going to be all the same value. All of that is 0 volts. It doesn't matter if where I stop, as long as I'm at the same node. Okay? All right. So now, okay, so nodes, I've showed you kind of how to label them. As far as color coding is going to be the easiest way to kind of see what those nodes are. So if you color code and then look at each one. So in here, the red one on the top here is what? Is that an ordinary or extraordinary node? It's going to be ordinary because there's only 2 elements connected to it. What about the blue one? Ordinary, good. This blue one? Correct. Green one? Perfect. And red. Okay, you guys are getting this. Okay. Green one here? Extra, correct. Purple? And green, or red. Awesome. Good job. Okay. How many nodes does this circuit have?
3, 4.
Okay. I haven't started the poll, so we are trying to move a little quicker today, so go ahead, and if you don't mind raising your hands, who thinks it has 2? Okay, who thinks it has 3? Okay, who thinks it has 4? Okay, who thinks it has 5? Okay, very varying answers here. So how do we know? Coloring them is going to be the easiest way. So this would be one node. This would be another node. This is going to be a different node. And then I put there not connected, meaning that that green doesn't go there. So that one is going to be another one. So, sorry, what was that question? Correct. Yep. So the other way you may see this drawn is that it may have like a little loop over it too. And then that would not be a connected one. If it has a dot, that would be a connection. So in schematics, you're going to see a lot of times they'll just overlap the wires, and most of the time they will not be connected. Typically, you like to put a dot to differentiate that. So, great job for those that answered 4. If you didn't, hopefully you can see now why it is 4. Any questions on this? Okay. Okay, series and parallel. So in series, the way to remember this is that they are connected by an ordinary node.
Did we have to submit that?
No. I'm going to skip a couple of them just so we can keep going really at a good pace. So connected by ordinary nodes is the easiest way to differentiate this, which means coloring them first and then seeing. That coloring is usually very helpful at your stage to be able to look at and move things around to see like, oh, these are the same or not, and then it really highlights that. So really highly suggest if you're writing on paper, make sure you bring some colored pencils. If you have iPads or tablets, that's a little bit easier to color them. But either way, do come with coloring pencils and do them in your exercises. Okay, so coloring these, we have this one, and this one here are all nodes. So are all these elements in series? Yes, because each connection in between each one is ordinary. So ordinary, ordinary, and ordinary, and so this is all in series. All right, again, as I said, it doesn't matter if you have a bend in the wire and where that location is. The circuit next to it is actually exactly the same. So they're drawn differently, but they are actually the same function. Same currents going through them. It's just that you have bends in the wire. So this wire is the same as the other one. This is the same as that straight one. And then this is the same as the green one. Okay? All right, they each will have the same current going through because they're all in series. So same current goes through them. All right, in parallel, same extraordinary nodes on the top and bottom. So on both sides of them, you have to have the same colors of extraordinary nodes. So when I label this one, this is all the same nodes. I'm going to do them here. Different color here. And you hopefully can see, yes, connecting between the voltage, the resistor, and the resistor, you have the same blues on top and the same yellow is on the bottom. So those elements are all in parallel to each other. This one is a little bit more confusing to students because you kind of have unknowns over here. So when you see this, that means that there is, like it's taken out of a circuit and that most likely there's going to be connections there, which give you that third connection at those locations. So when you see something that's labeled A and B, that means that it was taken out of a circuit and there is an assumption that more elements are connected there. So you then treat these as extraordinary nodes. Okay, so when you see something that says A and B or just wires there, you're going to assume that there's going to be more connections and you can treat that as extraordinary.
Will it always be clear when there's an extra connection, or sometimes is it not obvious?
I'm going to try and make it clear if I ask you a question for an exam or something, but you kind of want to take into context when you move on, like, what am I trying to do with this? Sometimes you'll try and take a piece of a circuit that's really complicated and simplify it. And so with that, you're going to take it out from those connections. So because you took it out, you know it's connected to other things. So then you know as the designer what's going on. I'll try to make it very clear. All right, other questions? Yes?
Do we assume they're connected because it's only like 3, like there's no dot there? So we assume it's connected?
So it's only when you have wires that are crossing over. If there is, like there's not a wire that crosses, you can assume it's connected, yeah.
Okay.
So it's only the crossing ones that you would want to make sure there's a dot in between those. All right, any other questions? Okay, so for this connection, everything in parallel is going to have the same voltage across it, right? If I put this as my reference ground, you can see that, yes, this would all be the same value as V, because it's going to be set by that battery, and across all of that node has got to be the same voltage because it's the same voltage in all the wire. Does that make sense? All right, so these are called equivalent resistances. Okay, I think we've got time. And with equivalent resistances, oh, let me go back. Sorry. So, well, I'll do them here. Okay, resistors in series. You're going to add the values together. For resistors in parallel, it is going to be 1 over 1 of each of the resistors. So if I have like R1, R2, R3, R4, R5, R6, it would be 1 over R1 plus 1 over R2 plus 1 over R3, so on. So I'm going to do a little dot for as many resistors as there are in parallel. So sometimes you're going to see something a little bit more complicated where you're going to want to try and reduce first as many resistors as you can. So in this example, you're going to color it first, and then you're going to see, do I have resistors in series that I can combine first before I then look for those that are in parallel? Okay, break up into small groups and try and solve these 3 problems for the R equivalent. which is going to be the resistance that if I measured with a multimeter, I would measure from A to B between those 2 points. So find that R equivalent for all 3 of these. And then once you do, go ahead and use the poll to put the answers in. Yazan and Ian, if you guys want to walk around, and the TAs will be walking around if you have any questions as you're doing this. All right, so the answer for the first one should be 3K. So you add those two, they're in series. For number 2, they're in parallel, so 1 over 2K plus 1 over 2K would be 1K. For the third one, you're going to add the ones in series. So you need to identify that R3 and R4 are in series. And then R1 and R2 are in series, so that would be 4K plus 1K for 5K. And then as you highlight these, and these are ordinary nodes for the pink ones, and then this would be, again, an ordinary node because the A was just going to connect to something else. So you're going to have, hopefully you can see the blue and the yellow has two different paths. And so those two paths are going to be in parallel to each other. When you combine them into one, then you would just have a series connection. So this is in, this path is in parallel to this path. So you're going to have 1 over 5K plus 1 over 5K, which will be 5K over 2, and that will be 2.5K. And then you would add those all together. So it would be 5K plus 2.5K for 7.5K. All right, any questions on that? Yes?
Why is R2 and R1 not in parallel with R3 and R4? Because it splits up.
Okay, so you have blue on one side of them, but on one side of the other one is green, and then on the other side is yellow. The B node and the A node are different nodes.
Oh, okay.
Does that make sense? Because you're measuring it from one location to the other location. So there'll be different nodes, so they're different colors.
Okay.
And that is the only reason why they're not. If it was the same color, yes, they would be. But because you're looking at it as a measurement from A to B, they're different nodes. Okay, any other questions? That was a good question, though. Common question. Okay, what about batteries that are in parallel and series? So, again, remember with batteries, from here to here is only going to be 1.5 volts. But if I put this as my reference point of ground at 0, and then up to the top it would be an addition of each one. So you add. So they add in series. When you have them in parallel, remember we said that the voltage has to be the same in parallel at each node. Well, what if I put a 10 volt, a 1 volt, and a 2 volt? Any thoughts what's going to happen? I'm going to create a fire. Yes, correct. I am going to create a fire. Do not do this. Ouch. So what actually happens is there's a little bit of internal resistance in between these. So for a minute, they won't blow up, and then the 10 volt will overload the rest and blow it. So especially as you get higher voltage. So don't do this. So do not connect the same voltages at the same nodes. So you want to have resistors in between them to make sure there's a good buffer, and not a small resistor either, because it will melt it and blow it. So cannot have batteries in parallel to each other, okay? All right, so.
If they were the same voltage, do you connect them in parallel?
Yes.
Okay.
And that actually is used to help keep the batteries, because it will only draw so much current from each one. And so it can be a technique to actually help keep the batteries longer.
Is that how like balance charging works too?
A little bit of, yeah. So it kind of helps to balance. There's other circuitry that you want in there, but yeah. It's kind of, there's some techniques in that to be able to utilize both so that they don't diminish as quite as quick. Okay, wondering if I have time for this. 25, 30. Okay, let's just take 2 minutes. and work on these. So identify and label all the nodes and identify which elements are in series and which are in parallel. So when you look at those, you would say, like, I labeled them element A, element B, element C. So you would say, like, element A is in series with B, and then those two would be in parallel to C. So that's how you're gonna kind of label those. So go ahead and work in your groups for a minute. And then if something is not possible, then kind of cross it out and say unfeasible. So she's done.
Yeah, she finished in like 25 minutes. The only issue was grade scope. They didn't have an assignment for her to actually post the submission. So she said she emailed. I told her to email it to you.
Okay. Yeah, it was under exams. I thought it would show up also.
It didn't show anything on grade scope. It was just like empty. So at least on her end, she was showing.
Okay.
Or maybe it was something that I didn't see either. But yeah, she said she sent it to you, and then
Okay. That's fine.
yeah, and then the exam is in your.
Okay. Thank you so much.
Yeah, for sure.
Do you want them to put like stuff in parallel in series or
Just identifying.
just identifying?
Yeah. Just identifying which pathways. So like say.
Like the ENF.
Yeah. Yeah. A good question that I wanted to address, I forgot to mention this. So when you have elements that are in series, you add. So the plus sign is the notation. So you would have the plus sign for add, and then the parallel sign is two little lines next to each other. So that is for parallel. So those are the notations for parallel, and then series is add, the plus sign. So somebody was asking me this. So if you were to identify the series, you would say A plus B. And then if in parallel would be E parallel F. So those would be the notations you would use to write those elements. Okay. All right. Keep working on it. One more minute. All right, so take a minute to check what you've done, I guess, and see if you've been able to get. So these are the ordinary, extraordinary, E for extraordinary, O for ordinary. The components in this first one that are in series is going to be A and B, and then only once you combine would you have other things that would be in series with them. So you would first have to combine them into something, and then they could become series. Otherwise, just A and B looking at that is the only ones in series. Parallel would be that E and F, and then A plus B, so the A in series with B is going to be in parallel to C. So you would have to combine those first, and then it would be in, those two in series would be in parallel with the C. For this one, the ones that are ordinary would be A and B again. And then you also have the ordinary node of E and H. And then the series, or in the parallel ones, you're going to have, do you have any? So not without combining things, right? You would have to combine things first to then put them in parallel. So if I combine this, I would have that in parallel with F. Otherwise, that's really the only one. All right, any questions on this? Yes.
What about the first example?
On the 1.51?
Yeah.
Okay, what about it?
What about the, it should be included as a series between B and D.
B and which one?
B and D, in the first figure.
I guess I don't understand what your, which elements?
B and D should be in series 2.
Oh, they won't because of the extraordinary node between them. You can only have series if they're ordinary between them. Does that make sense? Okay. Yes.
Then wouldn't it be parallel with something? D?
So again, parallel, you have to have the same colors on both sides. So on the left of D is yellow, on the right is pink. Is there any other elements that have yellow and on one side and pink on the other? No, so they're not.
So D is neither in series or parallel.
Correct.
After you combine E and F,
Oh, sorry, just one sec. Let me have him first. Yeah, you're good.
so E and F are in parallel, and then wouldn't that be in series with D?
Correct.
After those are combined?
Then that whole unit would be in parallel with C. So we asked if you combined all of these by saying that E and F were in parallel and then added in series to D, that whole unit would be in parallel with C. Do you visualize that? Okay. All right, question in the back. Sorry that you got.
Can we combine them like that into ordinary node, or can we combine ordinary nodes too?
So first you want to combine everything in series, so that would be ordinary nodes. So look at ordinary nodes first. Can I combine anything with ordinary nodes, which means they're in series? Then you would look at if they're in parallel after that. Okay, yes.
So if C is then parallel with D, E, and F, you would combine them. And then wouldn't that mean that A plus B and then that mini thing is now in a series?
And then it would be A, B, and then this whole thing.
Yeah. So why do you have it, why is it written down at the bottom that A plus B is parallel?
Oh, yep, sorry.
Okay.
I'll erase that one. That is not correct. Okay. All right, other questions? Yes.
Partial credits on that exam?
There's partial credit, yes.
Okay.
Yes. All right, any other questions? Yes. So it is in parallel with C, but it's also in parallel with D plus E and in parallel with F. So it was correct to kind of say it was in parallel, but it wasn't all inclusive. So that's why I erased it. So to be more accurate, it is including everything off of the wire on the yellow wire. So that would be like a fully correct answer to get like a full resistance network. But it isn't wrong to say yes, those are still in parallel. It's just not the whole picture. Okay, property of parallel and series. So if Vs is 12 volts, what is the voltage across this resistor? Good job. Positive, negative. How do you know?
The sign of the battery.
Correct. The sign of the battery and the sign of the polarity of what's labeled. So here you can see that they're the same. So yes, this would be plus 12 volts. What if instead of this one, I labeled, I'm going to change the polarity on this one. What if this was my given label for V4? What would it be? Negative 12 volts. Okay? So you want to be careful with that.
So does that mean those two batteries cancel each other out then?
So they don't cancel each other out because they're opposite polarity. So if I'm to measure with my multimeter here, my red wire, and my black wire, it's going to be from here to here. V2 is 12 volts, Vs is 12 volts, V4 is actually opposite, so it's a negative 12 volts, which is also going to measure a positive 12 volts.
Oh, okay. It's a double negative then?
Yep, it's a double negative because where I'm putting my probes are going to be opposite what that label is. Okay, series, is this, what is going to be the value at this node if I put my ground reference here? Correct, 5 volts. What about this one? Can I have the 3 volts in parallel with 2 volts? No, do not do. You will blow something up. There's some cool videos if you want to go watch some of people blowing up stuff like doing like this. The other thing it will create is an arc flash too if you have too small of a resistor in between there. And on power lines, kind of a cool little thing. Power lines, especially because they have such high voltage, you'll get the air, and as it gets statically charged from like lightning and other environmental factors, it will create enough of a resistance that it will actually create an arc, and you'll actually see. So if you want to go look those up, they're kind of cool arc flashes, and it will actually, you can visually see that arc flash of the electricity moving from one to the other. Kind of a cool kind of force thing, I guess. Okay, current sources in series. What does a current source do? It fixes the current in the wire next to it. So the whole pathway is going to be fixed by that current. If I try and put 2 current sources to fix that, it's going to do the same thing as the voltage batteries. No, do not do. This one isn't as dangerous because internally these are made by other components, and so they dissipate and will melt first before something happens. But you can't have them in the same wire, different currents. In one pathway, it has to be the same current. So if I have 2 currents, we're going to get to this next, they actually add up to what goes in has to kind of go out. As you think about these as water in a pipe, if they're coming in the same direction, they're going to combine and create more of a flow. So here I would have 5 amps coming in this direction, and going in this way I would have 5 amps. You guys have actually learned one of the first laws, which is Kirchhoff's current law. What goes in has to go out. That's all that the current law is. So not too difficult to understand, a little bit harder to do in practice, but But this is the simple idea of it, is what comes into an extraordinary node has to go out of the extraordinary node.
So it's kind of like an electricity conservation
Yep.
like law.
And that's Kirchhoff's voltage law. All right, so every element has a current and a voltage across it. So just make sure that you really think about that. So every element has a current. So what is the current going through here? Sorry. Zero, good job. It's zero, there's no current because it's open. But there, we would label a current there. We have no idea with this one because there's no voltage source specified. So it depends on what else is connected there. So you have to use the circuit to decide what the voltage is across both those.
Isn't that open too? So would it even have current going through?
So the current sources fix it even though it's open. They're actually like an internal source. So they have their internal source to create that current to make it happen. So just like a battery fixes the voltage, even though it might not be connected to other things, current source fixes a current. Once you connect it to a wire, it will actually push some current into it.
So where does it go then if it's, like where is the current going if it's just open right there?
So you do have to have some, like a load to draw it out of it. So you would have to have, a resistor to ground, and then your pathway actually is internal to it. So that's where there is still a pathway to ground. So it will create current going through that load, which a lot of times we will model by a resistor. Okay. All right, any other questions? Yes.
Are you assuming there's like a voltage in that too, or is there not have to be a voltage?
So there's always going to be a voltage across it. You just don't know what it is.
Okay.
So you can't say, oh, it's going to be 1 volt. It will have a voltage, and typically it will be really small if you don't have anything else connected to it, but there will be a voltage to it. All right, any other questions? Okay, so we're moving on to the first main law. It's called Ohm's law. And Ohm's law is a relationship of the voltage to your current and resistance. So it means that voltage is directly current times resistance. So this is called, it's linear. So as I increase my current, I increase my voltage. And it will be, if I was to graph this, as I change my voltage, I'm going to get a direct linear line of every change in voltage results in an exact similar change in current, and the slope of this line is it's going to be 1 over R. So I, if you solve this, is V over R. So it gives you a slope of 1 over R. So your slope is based on that resistor value. So if I know my voltage and I have just a very simple circuit like this that has a resistor, my current is just going to be voltage over resistance. So I get 5 over 5K, and it would be 1 milliamp. Okay? All right, your turn. So go ahead and find the currents. In this one, I1 and I3. And then if you're able to solve that one, try and solve these next two. All right, go ahead and again, introduce yourselves. I forgot to say that at the first. Introduce yourselves to your neighbors if you don't know your neighbor yet. And solve it, or talk to them about how to solve it. It's weird. Okay. I may not be able to do it till after class.
Because we only have one attempt allowed.
Oh,
Yeah, I don't know how to.
And then we did publish also, this is a discussion for the sponsors. Thanks. Okay, so for this one, You want to, it does not have a reference ground in there, so you want to always provide a reference to ground. So label something as 0 volts. So I always recommend the one extraordinary node that has the most connections. The other place you may want to put it is visually what's pleasing to you. So I like things on the ground, so, or on the bottom, so a lot of times I'll put my ground there. You get to choose, if it's not labeled in there, where your reference point is. So knowing that means that this battery is fixing this node all at 12 volts. So every current in here, this is going to be, and it's a plus 12 at that location. The direction of polarity of each of these is such because the negative is where the arrow is. So this I1 is going to have a plus 12 over 12 for 1 amp. This one would have 12 over 6 for 2 amps. This one again would be 2 amps. This one, though, for I3 is labeled going into the node. So this one has a negative, while this one is a positive. So they're going to be opposite. So this one would be 12, a negative 12 over 3 for negative 4 amps. Okay? So for the I times R, if it's the same direction, it's going to be plus. But if it's opposite, if they're opposite the voltage, it's going to be a negative. Okay? Any questions on those? Okay. This one, you're going to have the voltage across it. Again, these are going to be the same. So this are ordinary nodes, so these are in series. And if I put my reference on the bottom, that means that this is going to be a 1.5 volt value at that, which is going to be across this as a positive 1.5. My current is defined as going in this direction, same direction. So it would be 1.5 over 150 for, somebody get that? 10 milliamps? Okay. All right, this one again is in series, and the current is being forced to go in this direction. So even though there's a bend in the wire, it follows the same direction as the current source. Again, I put my reference point of 0 volts, which means across the 5K you'll have V1. So V1 will be 1 milli times 5K, and so 5 volts. Yes, is there a question? Oh, you're stretching. All right, any other questions? Okay. All right, next concept is power. So electric circuits transfer energy, and the transfer of energy is going to be watts times hours, where power itself is in watts. So the energy transferred is a per unit time is called that power. So watts per or divided by hours times hours is just going to be watts. So electrical devices consume or supply power. Makes sense, right? We have to have power to be able to make things work on our devices. So simple example, you have a battery, you have a light bulb, and a light bulb is going to consume your power while your battery is going to generate or produce it. So it supplies the power. Power is in, again, the watts. So W is that unit abbreviation. And to define or to calculate what power is, you just take the current in the element times the voltage in the element. Energy, again, is watt hours. And so it's the sum of a power, the sum of the power over a specific amount of time. That will be your energy. So consuming and producing, when you have the current and the voltage in the same direction, you're going to consume. When they're in opposite directions, they're going to produce. So all of these are valid ways of labeling current and voltage. The one that represents consuming is when they're opposite. Or the same. So this one is going to be the same. No, these are the same. And plus minus the same. All those are the same. Okay. All right. Okay. So this circuit has 9 unknown components. So these components could be resistors or voltage supply or current supply or some of the elements you don't know, which is an inductor or a capacitor. So find in the components 1 and 3. We're just going to do this pretty quick. So go ahead and try and find the power in the components of 1 and 3. And then if you want to put into the poll what those answers are. Okay, so let's see what the correct answers are here. So power is going to be that current times voltage. So for element 1, the current is defined as going plus to minus. So it's going to be opposite. So it would be a negative value. So for 1, you're going to have 16 times 4 and a negative of that. So that would be negative 64. And the units? Watts. Good job. All right, and then element 3 is the same direction. So the power in element 3 is going to be I, which is 1, times 10 for a plus 10 watts because they're the same direction. So what do you think element 3 is? A resistor or a voltage supply between those two? Plus means it's consuming power. So it would be a resistor. And this is supplying power. So this is most likely a voltage source. All right, there was a question. Did you? Okay. Any other questions on this? Yes.
So are those blue arrows like the direction?
Yes, so again, you can label current either on the wire. On this wire, it's going to be the same. Let me find one. What?
Across the blue
Uh-huh.
arrow.
So the blue arrow I just drew right next to the device. So again, it's going to be in between the extraordinary nodes. So that would be the extraordinary node, and this would be an extraordinary node. So the current through each of those is going to be the same. And so it doesn't matter if I draw it right next to it. I could draw it on this side of it. On this one, I could draw it here, or I could draw it here. They're all the same. Does that help visualize it? So I know that's really hard in this beginning stage to like start to abstractly realize like, oh, these are locations. It doesn't matter if there's a bend in the wire. It doesn't matter if this element's here and this element's here. It takes a minute to kind of get used to this abstract kind of thinking. And you guys will get it, just keep at it. Let me highlight. Okay, so this is negative and this is positive.
Okay.
So those are opposite.
Right.
So it's negative.
Okay. So you just switched, right?
So when they're the same, you just have a positive IV. When they're opposite, you have a negative IV.
How do we know what's negative? Just
By the current direction and the voltage polarity.
Oh, that red arrow?
Yeah.
Okay, I see.
So you were given 4 amps, so I just redrew it underneath to be right next to where the polarity was for the positive and negative of the voltage supply.
Oh, okay.
All right, any other questions? Fun. We're moving on to the Kirchhoff's laws. And so the Kirchhoff's voltage law, this is a visualization of the voltage law. As I've said before, like looking at it as height, what this means is that I have changes in heights and I take a full loop around. So if I go up the mountain and I go down, I got to go back up, and I got to go down, and I go back up, I go down, I go back up, I go down, I go back up, I go down, I go over, and then I come back down. I'm always getting back to the place I started, no matter what changes I have in between there. All of those changes have to add up to 0. So that's what that means. And so it's a summation of all the voltages have to equal 0. For the Kirchhoff's current law, again, water through pipe, rivers converging, ideal rivers converging, I guess, because you don't want to have any loss in there. But as you think about that, whatever comes in has to go out. So whatever goes into a node comes out of the node. So that mathematically is described as the summation of currents have to equal 0. Basically what comes in has to go out.
So basically the loss is negligible then?
Yeah, we're ignoring any loss going on in there. So these would be always ideal cases. So that is what these Kirchhoff's current and voltage law is. So there are different ways of writing the current law. I can define, and so this is up to you as far as what you prefer. So I'm going to show you all the different ways. As you label your currents that are converging into an extraordinary node or an ordinary node, ordinary is easy. Why? What goes into the ordinary node and what goes out is exactly the same, right? There's just one current that goes in and out of it. So that one's easy. You know the direction has got to stay the same. But when you have an extraordinary node, you may have a lot of currents coming in. So one way of describing this is to take the sign that's coming in, summing all of those together. So this would be minus I1 plus I2 plus I3 minus I4, and that equals 0. Or you can take all of the signs as it goes out of the node. So plus I1 minus I2 minus I3 plus I4 equals 0. Mathematically, these mean the same thing, right? You can take the negative sign out of all of them, multiply it by the 0, and it's exactly the same equation mathematically. It just depends on how you like to visualize this. Others like to visualize this as everything coming in equals everything going out of it. So with that one, you would sum all of the currents going in. So I1 comes in and I4 comes in, and then I2 goes out and I3 goes out. So that all of these, again, if you look at that, I can manipulate these other two equations to get the same exact equation. So all of these will be an expression of the same thing. It's just your preference on what visually clicks with you. So whichever one you like, practice them both, or all three of them, and then decide which one you like to use the most. And then just stick with that to get very good at it. Okay, so take a second and try to find in this one I2. It's always great to see a consensus. Like, I think everybody's on the same page. Good job. So note on this that even though this 120 milliamps is drawn on the bottom, it's the same current going through here, and it's the same current going through here. Again, it's got to follow whatever is the known information. So all of these are 120 milliamps. Here, 50 milliamps is going through this element in this direction. So whichever way you like to write it, I kind of have gotten more used to writing what goes in equals what goes out. So 50 milli goes in, and then I2 and I20 milli goes out. But it is not incorrect to say minus 50 milli plus I2 plus 120 milli equals 0, or 50 comes in as a plus, and then I2 goes out as a negative, and minus 120 milli goes out as a negative. So all those are the same. When you solve it, you get 50 minus 120. So you get a minus 70 milli. What does the minus mean? It's actually flowing in the opposite direction. What we're going to do, though, is still leave the arrow the way that it was originally put, and just put a negative 70 milli would be your answer. Okay?
So that arrow is like a trick question.
Not a trick question. It's just making sure you understand the directions. So you want to stay consistent. Again, just keep whatever you originally label and solve for, just leave it in those directions. So don't want to change the direction after that. Okay, any questions on this before we move to the voltage law? Okay. So the voltage law is the summation around a closed loop. So for this one, you want to pick a point of where you're going to start. So I'm going to arbitrarily just choose a point, and then you're going to move around the loop in whichever direction you want. I'm going to follow the way this arrow has gone, and what I like to do is circle my signs as I go through it. So as I move with my pencil, I'll put my pencil down, I'll move through this, and I'll circle the plus. I'll move through this, I circle the minus. I move through this, I circle the plus. Move through this, circle the plus. Move through this, minus. Move through this, plus. And then I'm back at my original point. Now it's easier to write my loop equation by just looking at the signs I circled. That would be plus 4 minus V1 plus V2 plus 6 minus V3 plus V4 equals 0. The other way of doing this would be to use the sign as you enter the element and do a minus, plus, minus, minus, plus, minus. And that would get through all of those elements. And then it would be a minus 4 plus V1 minus V2 minus 6 plus V3 minus V4 equals 0. And again, mathematically, these two equations are exactly the same. And so solving them, I could get the same exact solution. So again, it's whichever way you prefer to do it.
So is R4 actually a resistor? Because it's going from like lower to higher. It seems more like a battery to me almost.
So R4 is a resistor, and you don't know if the polarity is just labeled different. The current could be going negative, and that voltage is actually correct, but you don't know that till you solve the whole equation. So to solve this, you would have to put in, so you have V1, V2, V3, and V4, which are 4 unknowns. So in order to solve an equation that has 4 unknowns, you need to have 4 equations. So this would be 1. Your other set of equations comes from using Ohm's law. So if I labeled this arrow as my current direction, so if I labeled that I1, and I say I1 is actually going around in this direction, which would go through all of these, I'm going to see that V1 is actually, so the same polarity, so my Ohm's law is going to be plus. So I have V1 is I1 R1. My V2, the direction is this way, which has opposite signs, right? So because these are opposite, I get a negative here. So V2 is going to be a negative I1 R2. And then the current through R3 is again going to be the same. And through R4, again, I see it's opposite. So these are opposite. So for 3, it's going to be I1 R3, but for 4, it's going to be a negative I1 R4. So there are all my equations. I can substitute these in now and get one equation, one unknown, and solve for those values. Once I get current value of I1, then I can solve for each of these voltages. So this is how to solve this set of equations. Okay, looking at just the elements themselves, take a second to find out what V1 is here. More quick. That's great. All right, great job. So as I do a loop here, I'm going to pick again reference points. So I'm going to put that ground somewhere. And then I go through the elements. I would have a negative, negative, negative. And so V1 equals -4. Another way to visualize this is to put the ground at the negative side of V1. And then you could see, well, coming up to this node from here, my path is there, or it is through, starting there, I would have to go through as a -3, -1 for a -4 at that point. So whichever way you kind of visualize this is fine. It just is going to be more preference. I like the mathematical way, but some others like to visually see that that node has got to equal the other path to that node. Yes?
How did you determine which direction to point the arrows? Like
It arbitrary. So I could have done this. Let me do it a different way. So if I had gone this way instead, I'd have plus, plus, plus. This would be a +3 plus V1 plus 1 equals 0. And again, it would solve to be the exact same answer. So it doesn't matter which way you pick. If it's not labeled, you get to pick that. All right, other questions? Okay, so now we have one with multiple loops. So again, there's not a reference point labeled, so I'm going to pick one. Again, I like the ground, or the bottom one, so I'm going to put my ground down here. Highlighting these. This would be an ordinary node in between those two. So every element has a voltage and a current to it. So if it's not labeled there, you can label it. So here the I is going through this one as a label. It's already labeled in there, but here I don't have any label. So I'm going to pick an arbitrary direction of the current here. I don't know what it is, so it doesn't matter if I label it down or I label it up. I'm going to just call it a new variable. I'm going to call it I2, and this is going to define the direction of that polarity for this current. And then I'm going to just, again, arbitrarily choose the same direction of polarity for my voltage. If I did label it different and put plus and minus on the bottom and plus and then these two are the same, so that means that V1 is going to be a plus I2 times 3K. If I arbitrarily labeled it opposite it, I would need to do a negative I times R. So you just need to be consistent with what you pick. We don't have a current, so in this element, so we can choose that, which is also going to be the same current going in this one. In this one with a battery in there, most likely it's going to still flow from plus to minus, so I am going to have it go opposite in that battery. But it doesn't matter. If I don't remember that, it's okay. I arbitrarily label it the other way and solve the circuit. It will still work. I'll call this I3. And this now you can see across this one, these are going to be opposite. Across this, I don't have a voltage, so I'm going to again do it the same as what I labeled my current. So this would be V3. So I have how many unique currents here? I have 3 unique currents, right? I have I, I2, and I3. And that's, I have 2 extraordinary nodes, and I have 3 paths. So as I take loops, I'm going to just pick, I'm going to pick going in this direction first. So as I do a loop, I have plus 12, minus, and then again I have a split, so I could go either direction. If I go down through the 3K, that adds in an unknown, but if I go through the 6 volts, that's a known one. So as I take a loop, another strategy is to try to always take the loop with the most known information in it to reduce your variables. So I'm going to pick going through this one. So that loop will be plus 12 minus V3, which in a shortcut way I can just substitute in my IR right away. So that will give me I3 2K. So remember, these are equal. That doesn't look equal. Put it equals. There we go. And then minus 6 equals 0. So this makes it a little easier that I can immediately solve. I3 is going to be 6 over 2K for 3 milliamps. And knowing that current, I can solve, well, I can't solve quite yet. So I need to know what I2 is in order to find I. So do I know the voltage at this point? The pink wire is going to be what? I heard somebody say it. Say it loud. Good job. It will be 6 volts there. And so knowing that voltage, we can solve for I2 right away. So I2 is 6 over 3K for 2 milliamps. And then we can solve for I. So I3 comes in, I2 and I1 go out. And so I can solve that now with these values. This is 3 milli is equal to 2 milli plus I. So I is 1 milliamp. And then V3, so we already said V1 is what? Anyone? 6 volts. So I can get that by either saying like, okay, I know in parallel this wire up here has to be 6 volts because of the current of the voltage source, and then on the other side is 0. So I can visually see that it's 6 volts, or I can take I2, which I solved as 2 milli times 3K, which will also be 6 volts. V3 is going to be what? So 2 ways I could look at that. This side of it is what voltage? 12 volts there. And what voltage do I have on the other side of it? So I can say the plus side is here and the negative. So if I am looking at the plus side as my red multimeter lead and the negative as that ground reference, then I have 12 minus 6, which would be 6 volts in between there. So that's one way of looking at it, is 12 minus 6, or mathematically, I could go back to saying it's I3 using Ohm's law times 2K, and I3 we found as 3 milli, which will also give me 6 volts. So either way, this is a nice one because you have a couple ways of checking what the volt value is. Okay, go ahead and work on these. This one you're going to do the currents. This one you're going to do voltages. And we'll do like 4 minutes of this. So go ahead and try and solve for the currents and then for the voltages. I was so hoping we would get to be able to build today, but I'm like, I don't know if we're gonna have time.
Oh, 20 minutes left? Or less?
Yeah, I think we only have like 15. Yeah.
So, remember how you said that there was that one TA that was like gonna take over my lab after September 15th?
Uh-huh. Yeah.
Should I don't know how they are.
Oh, it's Brian. Do you know Brian? Brian Rasmussen. He was the one that brought him up.
Oh, okay, yeah. I mean, should I like swap a lab session with him? Or?
No, he's just doing class only. So he doesn't have a lab section. He's just doing class. So he's good.
Okay.
He'll just do it.
Yeah, it sounds good.
I just guessed.
Yeah, if we want to like replace for
Yeah, he's good. No, he's good. I was laughing. Liz told me, and she's like, every single one of your TAs. I'm like, great job, every single one of our TAs.
I spoke to Liz, and I was just like going down the list. I was like, is Kyle in the sheet?
Yeah. So she's like, I think every single one of your TAs. So I was like, oh, well, some people do it. Like, no, I guess not. They can all go. So anyway, I asked the other TAs. So Brian's over there, and Rebecca's over there.
And also, is there going to be a class for 12:35?
We'll be fine. Yeah, there was. Yes, I was gonna try and figure out placement. I thought there'd be like 40. Like 70, so we'll see how many afterwards. There's definitely gonna be a I think it'll end up being fine.
That's what I would do.
All right, so hopefully you've gotten similar answers to mine. So I2 would be 15 milli, I3 minus 5 milli, I4 45 milli, and I7. Note that I7 is the same as I1. Why? It's in series, correct, which means it's in the same path. So that path has one unique current. So remember, a path is between two extraordinary nodes. So this would be extraordinary and this would be extraordinary, so that I1 and I7 is the same current that's actually just flowing through this one element. This is a capacitor, by the way. So just an element going through those. All right, questions? Yes.
So So with I2, if it's 15 and then it combines with the -20 from I5, that would make -5.
So this one is going to be, if you have, you were saying I3?
Well, so with I6, it's 35 going like upwards, right? And then I5 is -20. Those would combine like in the junction to make 15 going to the left, but I2 is going to the right.
Negative 15.
I2 should be negative 15,
Yeah.
so sub 0.
Yes. Thank you. So I2 would be a -15, yes. I miswrote that. I wrote the equation right, but I miswrote it here.
That would change I3 as well.
Yep, yep. Oh my. This is not going, there we go. Okay, so this is a plus, and this is a negative. Oh my, not working with that one. Okay, yes, so negative, okay, solving that equation, this was supposed to be equal to 0, yeah. Okay, -15, and then where did, so this would be a plus 15 for 25. Is that correct now? Thank you for catching that. Good job. Okay. Other questions, comments, mistakes that you catch? Yes.
Yeah, so for I2, or all that gradient equation, if all the arrows are just converging and like pointing to the same point, does that just mean it has to add up to 0?
Yep. Yep. So that's why I2 plus I5 plus I6 equals 0, was what that equation actually is. All right, any other questions? Okay, and then remember again that negative current in here of -15 milliamps just means like, yes, internally that's going to be flowing the other way. But again, for our analysis, we just leave it the way we drew the arrows in the beginning, solve it, and just say it's negative value. It's okay. Again, that negative isn't on that number line. It just means direction of flow. Okay, so for the voltages, again, I like to have a reference point. So I'm going to put my 0 volts here. And then labeling these, I already know, or highlighting these. I know the value for, what do I know the values for? So I know V5, V3, and V6. So V6 giving me that knowledge. I can see right here, I already know this voltage here as 3.2 volts. I know across V5 is 0.5 volts. So going from plus 3.2 plus a 0.5, this node here is going to give me 3.7, which is also the same voltage as V4 from here to here. And then V3 is 2.3, so then again I can go here to get 4, 5, 6. 6 volts on that yellow, which from here to here then is 6 volts. And then V2 is going to be the voltage difference between both sides. So the plus side to the negative side, which is 6 minus 3.2. So 2.8 volts.
How do we get the 6 volts for the VS?
So this is one way of doing it. the other way is to do full loops. So if I go in this direction, I would have plus, minus, and then I'm just going to pick this one as a minus. So this would be plus Vs minus V3 minus V4 equals 0. I know V3, but I don't know V4. So I need another loop. The known ones I know are, I know this one, I know this one, and I know this one. So knowing those, I could take the loop instead and go around all of those, which would be a Vs. That will not switch. Okay. Vs, and then minus, minus, and minus. So Vs minus V3 minus V5 minus V6 equals 0. So V3 is 2.3, 0.5, 3.2. And that adds up to 6 volts too. So either way you like to visualize it. The other way, V4 would be, an equation for V4 would be if I went in this direction, a plus V4 minus and minus. So plus V4 minus V5 minus V6. V4 is 0.5 plus 3.2, which is 3.7. And then the last loop for V2, going through as many knowns, would be to take Vs, V2, and then V6. So Vs, V2, and V6. And that loop would be Vs minus V2 minus V6. And so Vs minus V6 and 6 minus 3.2. And that gives me the 2.8. So you always want to try and take voltage loops, especially through as many known values as you can in the loop. All right, we ran out of time today to do building, so do bring your equipment and supplies on Monday, and we'll do some building on Monday and also do a review for Wednesday. So next steps, if you haven't yet, make sure that you take the quiz 1, 2, and then there is 2 quizzes today, quiz for the attendance and quiz for the week of the material. So take both of those. And then if you haven't read, make sure you're reading and doing any exercises in practice.